All right, now that we've seen how one would go about reinforcing a slope, how do you adjust the limit equilibrium method to account for the soil reinforcement? So there are two methods for adjusting the factor of safety as calculated by the limit equilibrium method. In method A, the reinforcement forces used in the analysis are allowable forces and are not divided by the factor of safety. Only the soil strength is divided by the factor of safety. In method B, the reinforcement forces used in the analysis are ultimate forces and are divided by the factor of safety. Both the soil and the reinforcing force are divided by the same factor of safety. Now, when we talk about allowable and ultimate forces, recall that when you stretch a material that then fails, in this case in tension, as the strain increases, you get to a peak strength, which is called the ultimate strength, and then it may taper off to a residual strength. Sometimes we call this allowable strength. And a lot of these materials are steel or plastic, and they do have both an ultimate strength and then an allowable or residual strength, which is lower. So that's what we're talking about here. So with the method A equations, it works like this. The factor of safety is equal to the moment's resisting failure, so that would be the shear strength of the soil, divided by the overturning force, the overturning moment minus the moment caused by the reinforcement. So you're basically reducing the driving force. And so a factor of safety then is S divided by tau minus R. And if you rearrange that a bit, if you want to do it in terms of like mobilized, this is the shear strength over here. The mobilized shear strength is equal to the the shear force required for equilibrium minus the reinforcement, the strength you get from reinforcement. So the reinforcement results in a reduction of the driving forces. With method B, we put the reinforcement in the numerator. So the factor of safety is the shear strength, the resisting moment, plus the moment caused by a reinforcement divided by the overturning stress. Or in this case, F is equal to S plus R divided by T. And so the shear stress required for equilibrium is equal to the shear strength plus the reinforcement divided by the factor of safety. So in this case, by the way, I said the shear strength. The shear stress at equilibrium is equal to the shear strength. S is the shear strength plus the resistance divided by the factor of safety. In other words, the reinforcement resistance results in an extra component of shear strength. So again, in this case, the reinforcement reduces your driving force, and in method B, the reinforcement increases your strength. So method A is generally preferred because the soil and the reinforcement materials have different factors of safety and should be treated differently. So in method B, we use the resisting force we use here would be an ultimate force, because we then divide both the shear strength and the resisting force equally by a factor of safety, whereas with method A, we use the allowable force, and then the shear strength has its own factor of safety. So that's why it says the soil and reinforcement materials have different factors of safety and should be treated differently. So method A is what is generally used in the calculations when you do reinforced slopes using the limit equilibrium method. And most slope stability software allows you to do reinforcement, including UTexas and the educational version of UTexas. And so in our in-class exercises, we will be going through several examples of how you would go about putting in reinforcement and then how that impacts the factor of safety. So, when you're dealing with reinforcement, there are several factors you need to consider. In a lot of cases, now if you have like drilled piers or concrete piers or piles, then it might be the shear strength that controls there. But in many cases, like geogrids and reinforced earth walls, it's the tensile strength of the reinforcement that matters. You also have to worry about things like creep. Creep is just a long-term strain that occurs due to sustained loading over time. You have to factor in that there might be installation damage, so include that in your calculations. How durable is the material? Is it going to corrode over time and lose its strength? What is its pull-out resistance? And how stiff is it, and how much strain will you allow in the slope? And in our previous video, we talked about reinforced earth walls. When they build those, they actually have them tilted a little bit towards the soil, and as the wall gets taller and taller as they construct it, it leans out a little bit. So they take into account the movement and the strain as part of the design. The long-term capacity of your reinforcement, factoring in these things on the previous slide, the long-term capacity has to be less than the capacity determined by short-term tensile strength, less than or equal to short-term tensile strength, creep, installation damage, and deterioration of the property. You also has to make sure it's less than the capacity determined by pull-out resistance and stiffness and tolerable strain. So that you have to put some thought into what that resistance is that you're going to count on. And of course, you want to be a little conservative when you do that.